Hey everyone, welcome to Notes 3.02. Today we're going to focus a lot about the Pythagorean theorem and also triangles in the coordinate plane. The Pythagorean theorem, first off, we can only use this a squared plus b squared equals c squared if it's a right triangle. Okay, so here when we have a right triangle, we have two legs, just like an isosceles triangle. The two equal sides in an isosceles are the legs. Here we have a leg and a leg. And from the right angle, the longest side, so not either of the two sides touching the right angle, that longest side is called the hypotenuse. So when we're looking at the Pythagorean theorem, that c value is the number by itself, a squared plus b squared equals c squared. That's always the hypotenuse. And a and b are the legs. So the a squared and the b squared, doesn't matter the order, but those are the two legs. So if your right angle is here, if this was 18 and this is what we were looking for, and we knew the length of maybe a ramp here was 50 feet, when we would go substitute into the Pythagorean theorem. So again, I made this up. Let's say we have the top of a building, we have a ramp, maybe it's a ladder, 50-foot ladder on a fire truck. I'm sorry, I hear beeping out my window right now. I'm thinking of a fire truck up to the top of the building. So if this is 50 feet up and this ladder is 50 feet long, we want to know, do we have enough clearance from here to the road? All right, so this is your Pythagorean theorem, a squared, b squared, c squared. So we would put in 18 squared plus b squared equals 50 squared. So that's your substitutions. So we're going to look at a few other examples here and solve them. Okay, this one I just wanted to talk about where the positions go. Since c is that hypotenuse, that's the 50 that goes in by itself, and 18 and the b can go in either place here and here. Okay, so looking at example 1, find the missing side to the nearest whole number or in simplest radical form. So looking at this picture, we have the two sides right next to my right angle, so we're going to call those our a and our b. And x is the hypotenuse. That's the side we're looking for across from the right angle. So in this case, we have 8 squared and 6 squared equals x squared, x being the hypotenuse measure we're looking for. In this case, we solve these using PEMDAS, okay? Parentheses first, exponent second, summation third. So PEMDAS. So there's no multiplication division here, but there is some addition. So 8 squared is 64. 6 squared is 36 equals x squared. From there, we're going to add these together. Again, we're trying to get x to stand alone, but we still have some combining like terms here. So 64 and 36 do add to 100 equals x squared. So now x is alone on one side. These are all combined on the other. Here we're going to take the square root of both sides. So when we take the square root of 100, we get 10 equals x. Now technically this is a plus or minus 10. Whenever you take the square root, we do get two values as an answer because x was squared, so there should be two answers. But since we're doing a geometry question here, this length from this point to this point can't be negative 10. So we're going to say here that x is 10 as our answer for letter A. Moving over to letter B. Just going to switch colors here. We have three sides. We know that this is a leg, so I'm going to call that one A. This is a leg, we're going to call that one B. I just go left to right. It doesn't matter where the A and B go because, again, here we're adding. It would have been the same if we had put 36 first and 64 second because a commutative property happens. But this 5 is definitely our C value. It's across on the right angle, so that has to go in by itself on the right-hand side. So here I'm going to write x squared plus 3 squared equals 5 squared. Now again, we want to get x alone. So we can't do anything with that. That's just going to drop down. But I can simplify 3 squared is 9 and 5 squared is 25. Again, to get x alone, we're going to subtract over our 9. X squared is 16 Therefore, x, when we take its square root, and again, if you're unsure about your square roots, your graphing calculator could help here. So I would press second here. X squared is down on that first column. And I put in 16. So square root of 16 is 4. So if you do struggle with those radicals still, we do get x to be 4 there. So that means that 4 squared plus 3 squared will give you 5 squared. Well, 6 squared plus 8 squared gave us 10. Okay. We're going to talk about these in a second with this word here, Pythagorean triples. That if I dilated and rotated this triangle onto here. So again, think about that. This triangle, ABC, I'm going to kind of cut it, my little post-it note here. That triangle, ABC, okay, can rotate itself. Let me actually flip this over. There's the 3. The 3, 4, 5. Okay, that kind of shows up nice here. This triangle kind of rotates. Now here it's the same size because the pictures could kind of get bigger or smaller. But these measurements are telling me that that one's 6 and that one's 8. Well, here it was 3 and that's 4. So this one does dilate twice as big. So if this hypotenuse was 5, this hypotenuse is 10. So those triangles are what's called similar. And that's another one of our units we're going to do in a few weeks. So again, we could dilate the images bigger, and we're going to look at similar figures coming up. Moving on to letter C. I guess I'm going to go back to purple. I was trying to look for more colors here. We have 2 sides. We have a 5, we have a 10, and we have an x. And we have to decide how does this go in. So our Pythagorean theorem, a squared plus b squared equals c squared. Remember the hypotenuse, which is across from the right angle, is our c value. That goes in by itself. So the 10 is going to go in over here. So we have 5 squared and x squared. And again, it doesn't matter this order. I could have written x squared plus 5 squared. But here again, we want to be getting the x alone. So we're going to square everything. So 5 squared, x squared is going to stay, equals 10 times 10 is 100. To get x standing alone, we need to subtract 25 from both sides. And we get x squared equals 75. Then when we take the square root of both sides, well here, leave it as the nearest whole number. Well, if I put in the square root of 75, okay, we get 8.66. So that could round up to 9, but we know that the square root of 81 is 9. So this radical is just a little bit smaller by a few decimals, okay? But it also asked us for simplest radical form. So the first 2 answers here came out nice. This one we are going to reduce. So we know that 25 goes into 75 3 times. So 5 square root of 3 is going to be our final answer there. And again, that does approximate to 8.660 if we needed a decimal form. Okay, so that is how we set up our Pythagorean theorem. The next few examples are going to be some word problems. We're going to look down at here. But these Pythagorean triples that I kind of have outlined in the middle of my paper, just want to draw some attention to them. So these Pythagorean triples is not necessarily something you need to know. It's just helpful to know that if you had the numbers 3, 4, and 5, those 3 numbers always make this Pythagorean theorem true. That if instead here I put in 4 squared plus x squared equaled 5 squared, the missing value would be 3, because these 3 numbers always make the Pythagorean theorem true. That 3 squared plus 4 squared always gives you 25, which is 5 squared. There's a couple other triplet numbers that work. So these are called Pythagorean triples. Another triplet that works is 7 squared plus 24 squared will always give you 25 squared. So 7, 24, and 25 will always work into the Pythagorean theorem. 7 squared plus 24 squared gives you 625. And then you take that square root of 625 and you find it's 25. So with that said, if you were missing any one of these three numbers in a right triangle, okay, let's say you had this side was 7 and this side was 25 and you were trying to find the third side, you could sub into the Pythagorean theorem and use it. But if you memorize this triplet, if you have 7 there, this side's got to be 24 to make that side 25. Okay. Another triplet that works is 5, 12, 13. Okay. So if this side is 5 and this side is 13, you could set up your Pythagorean theorem. But I'm going to tell you the triplet goes like this. If you take 5 squared and add it to 12 squared, you're always going to get 169, which the square root of 169 is 13. So 5, 12, 13 will always work. Now, similarly, like we had up here, the dilation worked, right? If this was 3, this was 4, this is 5, well, 6 is twice 3, 8 is twice 4, and 10 is twice 5. That if you dilate this twice as big, you get the same case. So if I made a bigger right triangle, okay, and said that this side was 10 and this side is 24, that's 12. 5 becomes 10, 12 becomes 24, therefore 13 becomes 26. So that's a triplet, but it's the multiple of a triplet. That if I multiply these all through by 2, we get a new triplet. Okay, so these are the simplest ones. There's one more right now that's escaping me. 8 squared plus 12 squared. No, that's not it. 8 squared plus 15 squared. I did have to cheat and look this up. Just give us 17 squared. So 17 squared is 289. So the other triplet there is 8, 15, 17. So again, these Pythagorean triples you don't need to memorize, but they're sometimes helpful with questions like number 13, or number 2, with the angle or a ladder measuring 13 feet. So a 13-foot ladder rests against the side of a house. The base of the ladder is 5 feet away from the house. Approximately how high above the ground is the top of the ladder? So this is a problem that firefighters do as they are trying to decide how tall is a building, where do we need to put the truck in order to have a steady ladder going up to the top of a building to rescue someone. So this math is done on a daily basis, this Pythagorean theorem. Same thing with stairs into a house, okay? When you have stairs, it's a rise and a run going up each piece of a staircase, okay? And the general shape of a staircase does have right angles, okay? Because the house and the ground are usually perpendicular. So when it tells you that the house is, the ladder is up against a house, we know that in order for a house to still be standing, it has to be perpendicular to the ground. So that's what's telling us that this is a right triangle. So it's kind of hidden within the question, and there is a diagram there to help us. The 13-foot ladder rests against the building. So again, we do want to be drawing pictures and labeling them appropriately. So the ladder is 13 feet. That represents the hypotenuse of our triangle. And the base of the ladder, so how far the base of the ladder is to the house, is 5 feet. Approximately how high above the ground does the top of the ladder reach? So we're looking for x here, which is the height of that ladder. So our Pythagorean theorem says a squared plus b squared equals c squared. Again, our hypotenuse is that 13 goes in by itself. The 5 squared and the x squared can go anywhere they want. Now this happens when I see that 5 and 13, my brain kind of has a little bell that goes off that says, oh, 5 and 13 are one of these Pythagorean triples. So I wonder if the third measure that we're looking for is the 12, the other leg, because remember the two smaller sides are your legs, the longer side is always the hypotenuse. So if we do the math here, 5 squared plus x squared equals 13 squared is 169. To get x squared alone, we have to subtract 25 from both sides. We get x squared equals 144. Well, magically, when we take the square root, we do get x to be 12. So we could have kind of skipped this work here, from here to here, if we had just said x equals 12 Pythagorean triple. Okay, so that can be a little shortcut if you memorize the triplets. You don't need these. If these don't make sense to you, that's fine. We'll be taking another look at those with our warm-up coming up later this week. Okay. Moving on to the back of the page. Triangles in the coordinate plane. Given a triangle ABC with the coordinates -2, 1, 1, 4, and 6, -1, use the distance formula to determine the length of each side. So what we're going to do here is graph those 3 points. A, 1 up 4, and 1, 2, 3, 4, 5, 6, and 1. So there's C, B, and A. So graphing those 3 ordered pairs, what we'd like to do is find the length of each side. So determine the length of each side. Leave as a radical and round to the nearest tenth. So we're going to find the length of AB, BC, and AC. Now, length, remember, is distance. So when I find the length of A to B, that equals the square root of, I'm going to use these ordered pairs. So we have x2 minus x1. So I'm going to write the distance formula way up at the top of my page. Distance equals square root of x2 minus x1 squared plus y2 minus y1 squared. Now this is something I know I tested already in the first unit, so I'm really going to fly through this. We have 1 minus -2 will give us 3 squared, plus 4 minus 1 also gives us 3 squared. So that becomes 3 squared plus 3 squared is 9 plus 9 is the square root of 18. So AB equals the square root of 18. Now, if I were to do the square root of 18 in my calculator, that also approximates to become, to the nearest tenths place, rereading the question, 4.2. That 4 does not make it go up anymore, so we're going to keep 4.2. So it's approximately 4.2. So I guess we asked for both answers there. All right. BC, from B to C. Now this is where I'm going to go over to the graph. Now, if I had gone up and over from A to B, it's 3 boxes up, 3 boxes over. I could have used my Pythagorean theorem because from A to B is the hypotenuse of that little green corner of a triangle. Okay, I'm going to do the same case from B over and down to C. So BC squared is my hypotenuse. Okay, from B to C is the hypotenuse of this right triangle. And we go over 1, 2, 3, 4, 5 boxes here. 1, 2, 3, 4, 5 boxes here is 5 squared plus 5 squared. Gives me 25 plus 25. So BC squared equals 50. And then we take the square root of both sides. So BC equals the square root of 50. Now, if you had used the ordered pairs, we have 6 as the x value of C and 1 the x value of B. Well, 6 minus 1 is 5. So you end up getting a 5 squared. And then -1 minus 4 more, because y2 minus y1 is also -5. So you get 5 squared and 5 squared somehow, some way. And then our square root of 50 becomes 7.07 as a decimal. So again, rounding to the tenths place, which is where our 0 is, that 7 rounds it up 1 more. So then BC equals, or is approximately, I should say, 7.1. And last but not least, from A to C, and this is where I'm going to use the Pythagorean theorem to help me again, I'm going to go down and over. So that's down, it looks like 2 boxes from A to C. And across 1, 2, 3, 4, 5, 6, 7, 8 boxes. So AC squared equals 2 squared plus 8 squared. So again, it went down 2 boxes and across 8 boxes. And again, if you need to slow me down, I went down 2 because this was up 1, that's down 2, or down 1. So 1, 2 boxes, and then 2 over, because I know I'm going from a 2 to 6. So I know the x direction is 8 boxes across. Okay. So AC squared equals 4 plus 64. AC squared is 68. And I kind of was a step ahead of myself there and put the square root of 68. So AC equals the square root of 68, which the square root of 68 approximates to 8.2. Okay. Now, where are those important? Well, we want to know what kind of triangle this is based on its sides. So kind of going back to our notes 3.01, are any of these 3 lengths the same? Square root of 18, square root of 50, or 8.2? No. So this triangle is going to be scalene. But looking at it, scalene, we don't know the angle measures. This angle looks acute, this angle looks acute, this angle looks acute. So we could say it's a scalene acute triangle, but we're going to utilize the Pythagorean theorem to determine if it's a right triangle. Okay? So in order to use the Pythagorean theorem to see if it's a right triangle, we're going to test these values into a squared plus b squared equals c squared. So meaning our first side is square root of 18. So one side is the square root of 18. The next side is the square root of 50. So this side is the square root of 50. So that's my A and that's my B. So A is the square root of 18. B is my square root of 50. And AC is definitely the longest, right? So that's going to be my c squared. So we're going to put that in for the variable c here. So your biggest one always goes in on the right. So if I substitute in the square root of 18 squared plus the square root of 50 squared, does that equal? So we're doing a test here. We're seeing if this side equals the other side. Does that equal the square root of 68 squared? Okay. Well, when you square radicals, it actually undoes the square root. So if I put in the square root of 18 and I hit squared on the outside of it, look at what happened. It becomes just 18. And again, the next one, if I put it in parentheses, the square root of 50, close parentheses, right, squared, because I'm substituting in the whole measure squared. Now, we don't want to take the decimal values. We want to take the exact values. So these radicals are our exact values here. But the square root of 50 squared is 50. Well, what's 18 plus 50? Gives us 68. Okay. So square root here technically undoes the squared. So we have 18. Square root squared kind of undoes itself, plus 50. Does that equal the square root squared 68? Yes. So what that's telling us is that triangle ABC here is a right triangle. Okay. One other thing we can do to find out that it's a right triangle is the slopes. If I knew the slope of AB is up 3 and to the right 3 is 3 over 3. And I know the slope of BC is rise 5 to the left 5. That means the slope of AB is 1 and the slope of BC is negative 1. That makes those lines perpendicular, which tells you that angle B is indeed a right angle. Okay, so these lengths, AB, BC, and AC all subtract into the Pythagorean theorem a squared plus b squared equals c squared does make ABC a right triangle. So it's scalene and also right because of our Pythagorean theorem. Example 4, using the coordinates of RST are -2, -3, 8 up 2, and over 4 up 5. Okay. And connected nicely. I'm actually going to use the straight edge this time. 1, 2, 3, 4, 5, 6. When you connect these, you can almost guess what answer it might be. Is this right, acute, obtuse, or equiangular? Okay, so we're going to have to go through and decide what option it is. Now, technically, you can't decide obtuse or acute based on this picture. Okay. Now, isosceles is not an option. Most of you are probably thinking to yourself, ooh, this side and this side look equal. All right. But what we're going to do here is the same thing we did up at the top. We're going to find the distance of R to T, T to S, and R to S. Okay. Now I'm going to go quickly here using our slopes and these right triangles I like to count in. So 1, 2, 3, 4, 5, 6 over, 1, 2, 3, 4, 5, 6, 7, 8 down. Well, that's 8 and that's 6 to find that hypotenuse there. So again, I like to find these little right triangles, over, down, diagonal. 8 squared plus 6 squared equals R to T squared. Well, I know 8 squared and 6 squared add to 100. We did this on the front page, equals RT squared. And to get the length of RT, we take the square root of each side. So RT is 10. So we know that this side here, R to T, is 10. Now looking at the next side, we have TS. And we can go over 1, 2, 3, 4 boxes and down 1, 2, 3. So this is 4, this is 3. So 4 squared plus 3 squared equals ST squared. So we get 9 plus 16. I'm sorry, 16 plus 9. My order is a little wrong there. It's ST squared equals 25. And when we take the square root of both sides, 5 is ST. That's another Pythagorean triple. So when you have a 3 and a 4, the third side automatically becomes 5. It works in the Pythagorean theorem each time. So that second side is 5. Now for the third side, we're going to go down from S and over to R. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 boxes over because R was to the left 2 and S is over 8. That should be 10 boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. So we have 10 boxes over and 1, 2, 3, 4, 5 boxes up. So RS is 10 squared plus 5 squared equals RS squared. So 100 plus 25 equals RS squared, 125. And we take the square root of each side. Okay. So I'm going to leave that as a radical because that does not come out nicely. It's not a perfect square. So we have RT, ST, and RS. Okay. And what we're going to do is we're going to sub in to A squared plus B squared equals C squared. So our longest side here is the square root of 125. We know that's bigger than the square root of 100. Okay. So looking at these lengths, square root of 100, square root of 25, square root of 125. This is definitely longer. So A is going to be my 10 squared plus B is my 5 squared. Does that equal the square root of 125 all squared? Well, this is 100 plus 25. Well, square root of 125 squared cancels out. So you get 125 there. So yes, those are equal. So since this side squared plus this side squared from the triangle equals the third side squared, this diagonal here squared, then those three pieces make the Pythagorean theorem true, meaning it must be a right triangle. Okay, so that's how we use our Pythagorean theorem. I just did it about 18 times for us. So looking at your classwork for today, classwork 302, for number 1, it's a right triangle. You're going to use your Pythagorean theorem. Number 2, number 3, okay, all the Pythagorean theorem. Again, here it asks you to round to the 100th. So we do want you using your calculators. Make sure your hypotenuse, your C is by itself. So x squared plus 6 squared equals 12 squared would be your substitution there, okay, to get you started. This baseball diamond question, baseball diamond has 4 right angles and 4 equal sides. So technically the distance from home plate to first base to second base to third base and back home is 90 feet per distance. So each side is 90 feet. What is the shortest distance from home plate to second base? So there you have a right triangle, okay? From home plate to second base, if this is home and this is second, this would make first base. You have 90 feet between home base and first and second. We're trying to find the distance it is from home plate to second base. How far would you throw that baseball as your hypotenuse there? So we can use the Pythagorean theorem to solve that word problem. Number 5 is very similar to last couple questions. You're going to find the length of each side, decide what kind of triangle it is. Is it a right triangle using the Pythagorean theorem? So that was just like questions 3 and 4, which should really be 4 and 5. Didn't we have more than 3 examples? That's okay. Examples 3 and 4 here. So you're going to substitute into the Pythagorean theorem. Question number 6 is similar to questions from classwork 3.01. You guys did very well, and same with 7. So good luck. Thank you for your hard work. We'll see you soon.